So, what do you mean by deterministic pushdown automata? A pushdown automata M is deterministic if and only if the delta transition contains no pair of transitions that compete with each other, and whenever M is in an accepting configuration, it has no available moves. For example, if Q is an accepting state of M and there is no transition like Q epsilon epsilon tends to PA for any state P or input A. Unfortunately, unlike FSM, there exist NPDPA non-deterministic pushdown automatas for which no equivalent deterministic pushdown automata exists. Previous examples which we have discussed and designed in the previous session are deterministic pushdown automatas, where each machine followed only a single computational path. But many useful PDAs are not deterministic, where from a single configuration there exists multiple competing moves. So, as in FSM, the easiest way to envision the operation of non-deterministic pushdown automata M is as a tree. So, this is an example of a tree wherein each node of a tree corresponds to a configuration of M, and each path from the root to the leaf node corresponds to one of the computation that M might perform. The stack, the state and the remaining input can be different along different paths. As a result, it will not be possible to simulate all paths in parallel the way we did for non-deterministic finite state machines. Let us take first simplest example of non-deterministic pushdown automata for the language consisting of even length palindrome of A's and B's, where the possible strings in this language are summation AA, BB, AAAA, ABBA, wherein AB is string W and BA is W raised to R. So, the definition of this PDA is M consisting of K summation tau delta S A, where K consists of S start state and F final state. Summation is A and B, tau both A and B symbols because we push both A and B symbols in the stack, and F is the final state. So, how do we design this language PDA for this particular language? Initially, we are in state S, and until we completely read this W, we are in state S and push all the symbols of this string W into the stack. So, the transitions are given at the state S. If the input is A or input is B, then push A into the stack or B into the stack. So, all possible strings of W, combination of A's and B's will be pushed into S. So, once we come at the end of the string W and the start of the string W raised to R, do not do anything, just move from state S to F with an epsilon transition. So, saying that here ends W and starts with W raised to R, and in final state F, for every match of the current input symbol and the topmost element of the stack is been popped and it remains in the same final state F. So, the delta transitions goes like this: first A or first B, push them into the stack, be in the same state S. Once you come across epsilon, that is mid of the string, then don't do anything, just change the state from S to F, and in F if there is match of the symbols AA or BB, then pop and be in the same final state. If we go for deriving a string, say the input string is AB BA, you can see here initial state is S, string to be read is AB BA stack epsilon. AB is the string W and BA is W raised to R. So, until you come across the end of W, that is AB, so A and B, so first A, S, A epsilon, A is pushed into the stack, then S, B, A, so this B also is pushed into the stack. Now, once you complete W and now you have come across an epsilon, then don't change anything, you can see here BA as it is, BA as it is, only change is in the state from S to final state F. And once you enter F, if there is match of the symbols in the input string and the topmost element of the stack, then pop it. So, again you see here F, A, A, again there is a match, pop it. By now you are in final state, input is consumed or empty and stack is empty, hence the string is accepted. But this language is non-deterministic, because there are, once I start reading a particular symbol of the string, before reading it I have two options, whether whether that symbol belongs to W or has come across mid of the string or it is in W. There are two possibilities. If it has not reached mid of the string, then be in the same state S and push all the symbols into the stack. Other alternative is, if it has come across mid of the string, then don't do anything, just take a epsilon transition, move from start state S to final state F, such that in F if there is a match, then the symbol from the stack is been popped and the string is accepted. Consider one more example wherein number of A's equal to number of B's. Here number of A's and number of B's are equal, but A's and B's can be anywhere. At that time the definition is K consists of only one state S and the first string is epsilon, so initial state is the final state. Input symbols are AB and tau symbols are also AB and final state is S. Here first, if I come across first A, push A into the stack. If I have first B, then push B into the stack. Else, if the topmost element is in the input string is A and topmost element of the stack is B, then pop the stack. Or if the input is B, topmost element is A, then pop the stack until it reaches the final state, consumes the input and stack is empty. So, we can see an example for the string AB BA. I am at start state S, input is A, stack is empty, then what to do? Push A into the stack. Next, I am at state S, if input is B, stack is A, so one A is paired with one B and this B is consumed and A is been popped. Now I am left with BA. Current state is S, input is B, stack is empty, then push B into the stack. And now current configuration is S, input is A, stack content is B, then consume A and pop the content of the stack. By now you have reached the final state, input string is consumed, stack is empty, hence the string is accepted. But this example of the language is non-deterministic, because for each possible move of A, there are two choices. Either if it is the first A, push that A into the stack, or if you are pairing that A with a B in the stack, then pop B from the stack. Similarly, If it is a first B, then push it into the stack. If not, you are pairing that B with the A which is on top of the stack, then pop A from the stack. So, for each symbol we have two alternative choices, hence the language is non-deterministic. Let us take one more language which is different from this, wherein the A region and the B region are different. It means I have a language wherein I have A raised to m and B raised to n, where m is not equal to n and mn are greater than 0. It is very hard to build a machine that looks for something negative like not equal to, but we can part this language into two parts. Break the language in two sub languages, wherein the first language is A raised to m, B raised to n, where n is in between 0 to m, and the second language is A raised to m, B raised to n, where m is in between 0 to n. So, when the string will be accepted and when the string will be rejected? If the stack and the input are empty, when it will be empty? When number of A's are equal to number of B's. At that time it will halt and reject, because I do not want number of A's equal to number of B's. But what I want is, if the input is empty but the stack is not, it means the number of A's are greater than the number of B's, then it must be accepted. The other way, if the stack is empty but input is not, it means the number of m are less than number of n's, that is number of A's are less than number of B's, then also the string must be accepted. For example, if this is your stack and the input string is AABB, as you have seen, whenever I come across a I will push that A into the stack. Again one more A, I will push that A into the stack. But when I come across B and if the topmost element is A, then this A is been paired with this B and this A is been popped and B is consumed. Next I have one more input A, stack symbol is, input is B, stack symbol is A, then what to do? Again B is consumed, A is been popped. Now you see here, it is in final state, assume it is in final state, input is been consumed, stack is empty, but will this language string be accepted? No, because the number of m is equal to number of n, so this must not be accepted. Take one more string, for example A, B, B. I have 4 A's and 2 B's. Are m equal to n? No. Then this string must be accepted. How? Push first A into the stack, then second A into the stack, third A into the stack, fourth A into the stack. Now I have a B and topmost element is A, so B is consumed, A is been popped. Again I have a B and topmost element is A is popped, B is consumed. Now input is consumed, it is in final state. Will this string be accepted? Yes. So this states that the number of A's are greater than number of B's. So what to do? So pop all these A's and go to the final state. Another combination where is here m was greater than n, so it is accepted. Another combination wherein the number of A's are less than number of B's, that is m is less than n, then also this string must be accepted. How? 2 A's, so first A and second A is been pushed into the stack. Next I have a B and topmost element is A is been popped, B is been consumed. Next again I have a B, topmost element is A, so A is been popped, B is consumed. Stack is empty, but input string has B's, that is number of B's are more than number of A's. So at that time this string must be accepted. How? By consuming all B's and reaching the final state. So here the first type, stack and input are empty, then it must halt and reject. If the input is empty, but the stack is not, then it is m greater than n, it must be accepted. The third one, wherein the stack is empty but input is not, at that time m is less than n, then also it must be accepted. So, let us design the PDA for this language step by step. So, first consider the case where n is equals to m. This is the same PDA as we have discussed in a raised to n, b raised to n. So, first what we do, all a's are pushed into the stack being at state 1. When I come across first b and the topmost element is a, then pop a and go to the final state. And if I have, this is for one pair of a and b. If more than pair of a's and b's are there, then being at the same final state in the self loop, given the input as b, topmost element as a, then pop a from the stack consuming b, be in the same final state. So, this is for n is equals to m. Now, these are the rules. Now, I want for first possibility m greater than n. M greater than n is what? Wherein I have more number of a's and less number of b's. Input is empty but stack is not. So, for this, so from first and second transition, first and second state, by now I have equal number of a's. So, equal number of a's and b's. Now, what happened? 4 a's are being pushed, 2 b's are being, 2 b's to 2 a's are being a, 2 a's are popped. Now, input is empty but stack is having a's. At that time what to do? You can just see the transition here. Input is empty, epsilon. I have a in the stack. This is the first a. Then what to do? Minimum one a is extra than number of a's and b's. So, what we do? We pop the topmost element, that is a, and go to the final state. So, this a is being popped and go to the final state. But still I may have some more number of a's, for which what I will do? Be in the final state itself, when no input, stack is having a, one or more number of a's, then pop those a's and be in the final state. Once you are in the final state, no input and the stack is empty, hence the string is accepted at the state 3. This is when m is greater than n. For the next and for the next condition, so these are the delta transitions. For the next condition wherein m is less than n. So, m is less than n means I have 2 a's pushed. When I come across 2 b's, 2 a's are being popped. Stack is empty, but I have still the input symbols bb. So, at that time what to do? So, 1 and 2, by this number of a's are equal to number of b's. Now, what happened? Input string has b, whereas stack is empty. It means what? This is 1 extra b, that is number of b's are more than number of a's. At that time, pop the topmost element of the stack and go to final state 4. Next, again in this state, if I have more than 1 b's, like in this example I have more than 1 b. So, what to do here? B in the final state, for this b, do not do anything, stack is empty, do not do anything, just consume the b until all the b's are being exhausted. You are in the final state, input symbols are empty, input string is empty, stack is empty, hence the string is accepted. So, this was for m less than n. Now, combining both together, the final language obtained is consisting of 4 states 1, 2, 3 and 4. Summation is AB, tau is we store only A into the stack and pop A when we come across a B, and final states are 3 and 4. So, 3 for if m is greater than n, 4 if m is less than n, and the delta transitions obtained are these. So, first and second transitions are, first transition is to read all the A's and push it into the stack. Second transition is for first A and B pairing. That is, first I came across a B into the input string and topmost element is a A, then go pop the A and go to state 2. Then in state 2, now I have 3 alternatives. 1, pairing A and B. Second, if number of A's are greater than number of B's. Third, if the number of B's are greater than number of A's. So, here we have 2 problems with m. We have no way to specify that a move can be taken only if the stack is empty, and we have no way to specify that the input stream is empty. Hence, as a result, in most of its moves in state 2, m will have a choice of 3 paths in it, 1, 2 and 3. Hence, it is non-deterministic. So, in order to overcome these problems, we go for using some techniques for reducing non-determinism. We saw non-determinism arising from 2 very specific circumstances. What were those 2 circumstances? A transition that should be taken only if the stack is empty competes against one or more moves that require a match of some string on the stack. Another is a transition should be taken only if the input string is empty, competes against one or more moves that require a match against a specific input character. So, let us consider case 1, wherein the problem is non-determinism could be eliminated if it were possible to check an empty stack. That is, when do I come to know that the stack is empty? And the solution for this is use a special bottom of stack marker hash. Like, so before doing anything, first what we must do is, the first transition must be to push hash into the stack. So, using this special bottom of stack marker, as I told, before doing anything, push this special character onto the stack. Then this stack is then logically empty when, if and only if that special character is at the top of the stack. And remember, before m accepts a string, its stack must be completely empty. So, the special character must be popped when m reaches an accepting state. So, the changes in this PDA is, we had 1, 2, 3, 4 states. Now, what is being stated? First thing is, before doing anything, push hash into the stack. So, we take one more state, 0 state. Now, instead of 1, this 0 state acts as the start state, wherein what we do? We do not do anything, we do not consume any input or check any stack, just we push hash into the stack representing the bottom of the stack, and then as usual we perform other things. Now, by using this hash as the bottom of the stack marker, you can see the transition back to state 2 no longer competes with the transition of state 4, which can only be taken when hash is the only symbol on the stack. So, only when hash is the symbol, only at that time we take the transition 4. So, there is no longer competition at state 2, but still the machine is non-deterministic because the transition back to state 2 competes with the transition of state 3. Why? Because of case 2, wherein the problem is the non-determinism could be eliminated if we were possible to check for an empty input string. how do I come to know that the string input stream is empty? So, for which the solution is we go for adding an end of the string marker. So, given a string AA, BB, so next at the end of the string we go for adding dollar, which represents end of the input string. So, applying this, we go for adding an end of string marker to the language to be accepted is a powerful tool for reducing non-determinism. Instead of building a machine to accept a language L, now what we do? We build to accept L dollar, where dollar represents a special end of string marker. So, by using dollar as a input end of the input string, so this is the PDA obtained. Now, you can see here, now the transition back to state 2 no longer competes with the transition of 3, since can be taken when dollar is red. Only when dollar is red, this transition will go to 3, and only when hash is been read in the stack, this transition will go to 4. Hence, there is no longer competition in between 3 different paths. Hence, this PDA is deterministic. The hash must be read on all the paths, not just for the one where we need it. So, quickly we will go through the stack, the same 2 possibilities where the input is AA, BB ending with dollar, and first what we do, from state 0 to state 1 we insert hash into the stack. Then as usual in the PDA, A is being pushed into the stack, second A push into the stack, third A push into the stack, and fourth A push into the stack. 4 A's are being pushed. Now, input is B, topmost element of the A stack is A. So, what to do? B is consumed, topmost of element A is popped. Then I came across a B. So, what to do? Topmost element is A, topmost element A is being popped, B is consumed. Now, you can see here I have input is dollar and topmost element is A. So, that is from transition 2 to 3. So, till 2. Now, at 2 you see here what is the input symbol? Dollar. And what is the topmost element of the stack? Topmost element of the stack is A. Then what to do? Pop A from the stack and go to the final state. Means pop A from the stack and where dollar is being consumed, go to the final state. But see here again, input is consumed, you are in final state, but still I have one or more number of A's and the end of the stack, that is hash in the stack. So, what to do? I need additional transitions, which are, if I have no input, dollar is also consumed, input is empty, stack is having A, then what to do? Pop A and B in the same final state. So, this will be for one or more number of A's. Then at last I have hash, which also must be emptied. So, you have one more transition here. Being at state 3, input is empty, stack symbol topmost is hash, then what to do? Pop hash from the stack and be in the final state. Now, what happened? Hash is also been popped. So, input string is empty, stack is empty, you are at the final state 3, hence the string is accepted. So, this is for number of A's more than number of B's. So, similarly for number of A's are lesser than number of B's. So, input ending with dollar and from state 0 to state 1 wherein we stored hash in the stack. So, again from state 1 to state 2, A is being pushed into the stack, another A is pushed into the stack, Next I came across a B, topmost is A, pop, again a B, topmost is A and then pop. Now what is the scenario? I have hash in the stack and B is followed by dollar in the input string. At that time we need 3 possible moves from state 2 to state 4. That is, in the input I have a B, stack is having hash, then what to do? Pop hash and go to final state 4. That is, pop hash for this B and go to final state 4. Now you can see here stack is empty, you are in final state, but still you have one or more number of B's followed by dollar, which also must be popped. So for these two I have 2 transitions here, that is, you have input symbol B, stack is empty, then what to do? Pop the stack and be in the same state. Similarly, once B stack is empty, then what to do? B is consumed and be in the same final state. Similarly, at last stack is empty, input symbol is dollar, so be in the same state and consume the input string. By now stack is empty, input string is empty, you are in the final state, hence the string is accepted. So in this way we could reduce non-determinism by including the 2 special symbols, hash and dollar, hash representing the top of the empty stack and dollar representing end of the input stream. So this is how we can go for reducing, technique used for reducing non-determinism. At last, let us discuss about the power of non-determinism. Before we discuss the power of non-determinism, let us design a PDA for one more language. So for language A raised to n, B raised to n, where n is greater than or equal to 0. Is it a context free grammar? Yes. Have we written context free grammar for this? Yes. Then if it is a context free grammar, then we have a PDA for it. Have we written PDA for it? Yes, in the previous session we have written a PDA for the language A raised to n, B raised to n. Now if I just change this language to A raised to n, B raised to n, C raised to n, where n is greater than or equal to 0. Now is it possible for us to write a context free grammar or design a PDA for it? For example, what are the possible strings? N is epsilon. Next, if n is 1, A, B, C. If n is 2, A, B, B, C, C and so on. Now in the previous language, when the number of A's were equal to number of B's, what we did? N number of A's we pushed and n number of B's we paired with number of A's and we popped. That is, take one example for the string A, B, B, C, C. So what we did, when I come across first A, push A into the stack. Again first A, push A into the stack, consuming A. Now what happens? Input symbol is B, topmost element of the stack is A. Then pop A and pair it with B, this B. Similarly, input is B, topmost element is A, pop it. Now stack is empty and now I have n number of C's, that is 2 C's. But the number of A's, the count of number of A's and the number of B's is lost, which cannot be compared with the number of C's. Hence, for this language we cannot write context free grammar nor we can write a push down automata for it. But its complement, that is complement of A raised to n, B raised to n, C raised to n, for this language we can write a PDA. There is a PDA that accepts this language, wherein this language is union of 2 languages. First one is W belongs to ABC whole star, where the letters are out of orders, and second one A raised to I, B raised to J, C raised to K, where I is not equal to J or J is not equal to K. In other words, unequal number of A's, B's and C's. When we perform union of this, a straightforward PDA for this language is, it first guesses which condition to check for, then the sub machine do the checking. So, once we define that for the language complement of A raised to n, B raised to n, C raised to n, we can design a PDA. Now, we illustrate the power of non-determinism. This language is context free and we can design a push down automata. If I put the complement for it, then what happens? I get A raised to n, B raised to n, C raised to n. Is it context free? No. It means what? It proves that the class of languages acceptable by PDA is not closed under complement. Complement of A raised to n, B raised to n, C raised to n. This language is context free. But if I take the complement of this language, I will get A raised to n, B raised to n, C raised to n. And just now we have seen that for this language, we cannot write a context free grammar, neither a context free grammar nor a push down automata. Hence, this language is not context free and the PDA is not closed under